Yeah, so my name is Brett Cornick. I hold a graduate degree in material science from UCLA from 2018, and I just wanted to talk briefly. I only have about 10 minutes on what the greatest challenges for sustainability and for our Earth are for the future generation. And actually, the end of the last presentation leads well into what I'm going to talk about, because what I believe is the greatest challenge facing us will actually be policy and regulation and bureaucracy. A lot of the technologies that are needed for improving our world and for fighting climate change are already, available today, have already been proven in labs, and just for certain policy reasons or bureaucracy reasons have not been widespread or implemented. So for this talk, I was just going to go into 3 different technologies that have shown promise in the lab, and for one reason or another, usually a political reason, have not been widespread or implemented or researched further. And I talked similarly last week on these 3 technologies as well. So if you're seeing this again, I apologize. But this time it's focused a little bit more towards just sustainability on Earth. And so the first technology is for air purification, and this one is photocatalytic oxidation. And this technology relies on using generally it's titanium dioxide, which is a mineral. It's very widespread. It's found in things like toothpaste and paints. It's in a lot of things that we use every day. However, when it's heated to above 600 degrees Celsius, it takes on a new form, and that form is photocatalytic. And that means that when it's exposed to light, it energizes in such a way that it is actually able to remove volatile organic compounds, bacteria, and some viruses from the air and the surfaces that it's coated on. It has in the past been used and developed by NASA. They have little self-contained air filters that essentially use a honeycomb coated surface inside of a filter that is then exposed to UV light. And that is able to break down any pollutants and pathogens that pass by. So the difficulty with adopting this more widespread, even though studies showing effectiveness as the 70s and 80s, the biggest issues that it's faced is that it's invisible, and you can't really see that it's working when it's on a surface. And with anything invisible, everyone questions, well, how do I know that it's actually working and that it's effective? And while you can show test reports from small laboratory testing or certain ASTM testing that can check for photocatalytic activity, when you actually are showing a client or a government the product, they have no way of knowing that what you're saying is actually true. And so in order to improve the public image of this, it would require some kind of regulation or backing, likely by a large first adopter or by a city government. And there are projects in the world that actually utilize photocatalytics right now. There are a few buildings in Mexico. There is a roadway, I believe, in the Netherlands that uses cement that has photocatalytic material inside of it. So it is growing in popularity, but it's going so slowly. And also, how do you quantify the return on investment from having cleaner air? It's difficult to show exact quantitative numbers to the investment arm of a company on how they're making their money back because they have cleaner air for their workers and for their customers. So that's been a big roadblock towards the photocatalytics, even though they do show a lot of promise. The second technology is in energy. And this is, I chose to talk about the Molten salt reactor, which was a nuclear energy source. Well, it still is, it still exists, but it's a nuclear energy reactor that does not require a cooling water source. And that's because the energy source is actually a liquid itself. It doesn't use solid energy sources. So this was first established and researched in the 1950s at Oak Ridge National Laboratory. But it just wasn't really pursued to the level where we could actually get a large-scale reactor built in the United States. And part of the reason for this is the politics of the Nixon administration really are what put the final nail in the coffin for the molten salt reactor. One of the main reasons is this reactor must be attached to its own chemical processing plant, and so it can be much easier to siphon off weapons-grade materials from the reactor. And so if the technology is spread to other countries, it can be more difficult to know if they are enriching weapons-grade materials. There had also already been a pretty considerable research into solid fuel reactors. And so to backtrack on that research and pursue this new line would have cost a large amount of money. And then thirdly, meltdowns, you know, the most famous, of course, being Chernobyl, definitely destroyed the public image of nuclear energy in general, to where funding new research into nuclear energy became fairly taboo for a long amount of time, even though, ironically enough, these reactors are essentially immune to meltdown because their cooling source is the same as their fuel source. So if they're losing cooling, they're also losing fuel. And so a prominent scientist with the Energy from Thorium Foundation, he claims that if we had developed this technology, you know, starting in the 70s, then by the 90s, we would have been completely energy independent. But right now, even if a project was funded, which estimates are about $1 billion to get a fully functioning reactor up and going, and everything went perfectly, it would still likely be 15 to 20 years from being able to get this technology actually certified. So it's still a long lead time to have this actually work, even if we started funding it now and everything went smoothly. So currently China is leading the world in trying to develop this technology, and they had actually aimed to, by the end of 2020, develop the first large-scale reactor of this design. I'm not sure how current events have changed the status of that, but they are leading the charge in trying to develop this technology. And then the third technology that I highlighted here was for waste management. And there have been prominent studies that have used ash from solid waste, from incinerated solid waste, to create cement materials. And so basically it's just the reclaimed CO2 from the incineration of trash and waste can be used to make the base materials for cement. And these cementing materials can be made of upwards of 85% waste ash. And so there has been work done to mix this ash with current soil here on Earth, and also with soil on similar to what was found on the moon, to see if it is a possible technology for use for building materials on the moon. So this would, you know, obviously help solve our trash problem here, but also help create a new supply of building materials that are commonly used for us. And so here the roadblocks are, the primary roadblock is a need to join essentially two industries that aren't currently very related, and that is trash management as well as the cement industry. And right now the status quo of the concrete industry doesn't really have an issue that needs solving that would require us to fund this research or to change supply chains. There's not, not another clear ROI to make this change, even if it does look like a promising technology that can solve challenges down in the future. So even though all three of these technologies are promising, they have shown great results in the lab, there's lots of research behind them, it's really the policy and the regulations that will be our biggest roadblock towards adopting these technologies and other ones similar to them to help make our Earth more sustainable. And so I think that's pretty much my whole 10 minutes. So thank you, and I appreciate the time.
Thank you, Brett. Very, very informative. And we are running a little bit, dragging a little bit on our time schedule, but we are off to our next speaker. Stay tuned for more questions on the thread, Brett.
Okay.
Thank you again. Okay, so let's get back